First of all, the name is Lora. Today we're going to be talking about we're going to be talking about process injection, specifically in the distro of Linux. Many offensive write-ups, books, and techniques say that basically Linux process injection is a done deal. You learn LD preload or ptrace, which are the most traditional techniques for process injection, and those are the only injection methods. You learn them in a textbook manner, but when you deploy them in actual production environments, they always fail. Many of us are still in that old mental state that Linux doesn't have any sort of protection. They don't have any EDRs or these telemetry stacks protecting them, but in reality, they do. You can just deploy an injection with ptrace and something just running CrowdStrike Falcon, it's gonna be detecting it. So there's like two failure cases. Either you inject it, the process crashes, and someone gets paged at 2 a.m., hey, this process crashed. Or the EDRs is gonna fire within seconds as it notices something off. Basically, the tool we're gonna be touching upon today is Aether. It's a specific injector built in Rust and C, which are aligned between an FFI boundary. We're going to be talking about how you wrap something in C, how you wrap C, which has a lot of memory issue leaks, but is the best at doing low-level calls, functioning with the kernel itself, wrapping in something in Rust, which has the same low-level capabilities, but it actually has the error logging, and it doesn't let the tool deploy if it doesn't work for that specific environment. Shortly, who am I? I'm just like a low-level fanatic. Mainly my background is in software engineering and development. I'm kind of active in NGOs or local DEF CON groups where we deal mostly with software, hardware development. Also part of a CTF group for participating in CTFs and hacking. I have background in technical work, but also actually organizing kind of meetups and conferences myself, mainly on a smaller scale, but I do have experience in that. Let's touch upon the modern, apologies. Okay. Let's touch upon the modern security landscape. Basically, as I mentioned a bit earlier, many of us still think that Linux servers are dead, they're unprotected, and once you're in, you're basically invisible. But no, we have many tools known as audit, which it logs the process creation, privilege changes, any syscall activity. We also have fnotify, which basically gives the kernel permission to access the file system before you can access it yourself. So it stops you from interacting with the file system before you can actually inject your process into it. Of course, then we also have eBPF. It's one of the more modern things in IT, which basically changed the entire field. Now, security vendors, they can hook directly into low-level kernel functions and protect ptrace, execv, and map without overriding a kernel module, and that changes the field completely. Tools like Falco, Pentagon, and other vendor EDRs, just any which come up to your mind, they're not just watching the logs which we have, like a normal script. No, they're watching the actual boundary at the lowest level of syscall. So basically, it isn't you just should avoid leaving files and forensics. No, every single syscall which you make in the system, it's being monitored against this type of baseline, which knows this is wrong and this is right. Basically, we have the Hall of Fame of traditional injection methods. These injection methods are the textbook ones. They're mostly the ones which are documented and known, but of course, as any, they have their own issues. We have the most classic, it's LD preload. LD preload is one of the methods which it basically, you set an environment table and the dynamic linker to load your SO file before anything else in that process executes. Well, it's probably one of the most best techniques for actually getting your injection done, but it's incredibly noisy in the way just in the environ folder and proc/pid, it's obvious. Basically anything which cats that specific folder and grabs LD preload, you're immediately, well, caught. So it's simple, useful, but it's loud. You can't hide from it. Then we also have ptrace, which is basically the fire and forget method. It's mainly used through ptrace attach, where you inject into a running process, you stop it, you override its information pointer, and then you try and return functionality back to the process. But this is usually the method which corrupts the original process, as you got something wrong in your stack. And when the process crashes, the entire production crashes. Then there's also one in many like CTFs write-up where people just try directly into the prog PID, basically to write directly into the virtual memory via its procfs interface. Basically, there's no direct injection needed into the process, but most of us, we don't have the privileges to do this to the file, and it still generates these detectable syscalls, which an EDR is trained upon, and they know this is bad. Basically, the problem is these are mature techniques. They've been used in the field for over 20 years, but at the same time, the blue team, the defensive measurements, know about these techniques for 20 years and created, well, tools to defend upon. And EDRs, these are one of the first rule sets they're kind of trained on. So, many classic injections fail today for a multitude of reasons, but mainly it's, first of all, we mentioned LD preload, it's really noisy. Then we also have the issue of the architecture. Let's say your injector, most injectors are built only for a specific architecture type. Let's say your injector is 64-bit, but you run into your target, which is actually 32-bit. Of course, a 64-bit injector can work against this 32-bit legacy process. There's also the issue, we know that most enterprise environments, they're a mix of architecture. You have maybe a 64-bit environment with this 32-bit SQL database. You also have the issue of like thread collections, mainly in ptrace. You enter the process, you have no idea what the process was doing before you interrupted it. It could have been in between a malloc call in C, and if you try returning it, you can accidentally free up memory space, which you shouldn't, and cause a crash in production, as I mentioned beforehand. We also have like the issue of RWX, read, write, and execute. If you try, for example, with ptrace and shellcode, that's one of the biggest heuristic indicators, which most EDRs will just flag them immediately. We already touched upon LD preload. It's noisy, and there's also like the thing that many high privileged targets or processes have this like already have a secure mode which immediately protects against LD preload. They don't even know it, they completely ignore it. We have the same issue, not the same issue for ptrace shellcode, but basically it could cause crashes if we don't know exactly the architecture or the information. So let's move beyond ptrace. We have many actually other methodologies which are way more modern. We have process VM, read V, and write V, which basically are like the key alternatives. They let these syscalls like let you copy data between user space memory regions of different processes directly. There's no attachment, no stage change, and no like tracer PID. So if you enter the prog PID status folder, there's no tracer PID. It basically is the same as before. But of course, it may be a key alternative, but it does have its trade-offs. You do need capsys ptrace, or like appropriate ptrace settings, which a few like specific distros or defense systems may protect against. So in those environments where these restrictions aren't restricting you from using this methodology. It's the way quieter, primitive, and just better. Basically, what Aether kind of focuses on is not just one specific technique. It uses ptrace when it can get away with it. It uses cross-memory writes if it can get away with it, or fully anonymous memory file loading. We also have something interesting. We can just eliminate the file on disk. We do this via mfd create. What we basically do is we create a file descriptor directly into the RAM. We inject it directly into the RAM. The kernel treats it like a real file. You can write into it, you can execute into it, but it has no system, but it has no path on the file system. Nothing in TMP, nothing in dev, sham, like knows that even it exists. And many tools such as Finodify and Innotify can't catch it. But of course, it doesn't mean it's completely invisible. In procpid, like in the FD and maps, it'll show an entry of mfd, whatever the name is of the file, and maps will also show this like kind of anonymous executable mapping. The plus here is, of course, it's a bit more hidden. There's no disk on the file, and you can write your disk directly into mfd and then call a specific function fxv onto the descriptor, or like map it into the target's memory address as an executable segment. What's an interesting part is actually choosing the process which you're going to infect is probably one of the more underrated things of process injection. Basically, we can hit some process that's going to give us temporary access into it for maybe about 10 minutes. But if we infect the init daemon, which is known as the process always with PID1, you're basically touching the tree of the root file system itself. And there's also the fact that if you infect the init daemon, all child processes are like spawned from it. So meaning you indirectly infect all the other processes and you just take over the operating system. The attack surface, of course, increases even further with this. You have the dbus IPC, which you could attack on. The systemd as a whole, which is systemd is usually PID1 in most modern distros. So let's just introduce Aether more directly as an injection framework. Basically, it isn't like a single tactic script. You don't just have LD preload, you don't just have ptrace or mfd. Pick one and like hard code it and just test through these bunches of virtual addresses and see if they're actually real. Basically, you have this C layer. The C layer is the one which injects into which is the parasite which is injected into the code. It has these function calls, while Rust, as a language which of course solves in the memory leaks of C, is the one which deals like the communication, does the calculation of the addresses, and if there's anything wrong, it won't inject, it will just abort the mission immediately. If we had an injector which was fully built in C, even if something was wrong during the process, it would still inject into it, it would crash the process, and we'd be, well, found. Basically, what the Rust does, the Rust and C, they communicate through an FFI tunnel, mainly through Rust and safe blocks. And at runtime, actually, Rust will be fingerprinting the environment, and it will check what the ptrace scope is, whether the BPF telemetry stack is visible, whether anything such as YAMA LSM is active, or other types of defensive measures. And then it'll choose the most definitive injection method, ptrace, or like around 20 injection techniques. Now we do have a bit of a problem again in the 32-bit and 64-bit. We don't just have the issue of it being a different process, a different type of structure. Of course, ELF headers, they're different. So basically, throughout with Aether, we just calculate the ELF if it's something which we can inject into with a 30-bit, 32-bit, or 64-bit injector. We also have binary layouts. Over here, on 32-bit, the first 4 registers, EAX, ESP, EIP, EBX, are far different than the first 6 register widths on 64-bit, ROX, RSP, RDX, RCX, etc. And in 32-bit, the register constraint, they are 68 bytes, while on 64-bit, we're dealing with a technology which is 216 bits. So imagine your 64-bit injector trying to write into a 32-bit process which only accepts 68 bytes. Of course, it's going to get confused, and the process is immediately going to be crashing. Let's just go directly into the C layer. Basically in C, as we mentioned a bit earlier, we're going to be avoiding... the C is like as minimal as it can be. We have no malloc, no printf, no memsp, which is pulled from the standard library. The reason is mainly that if you're in the operating system and you kind of inject with these libraries, their function calls are very known, and the symbols are very detectable. There's something which most EDRs, that's one of the first things which they are trained on. So of course, we're going to be trying to bypass libc entirely and use memory operations which use... Oh, damn. Which use pointer arithmetic rather than the standard library calls, which most defense systems are trained upon. We also have the function mechanism. The function mechanism is, we have the PLT, which is the procedure linkage table, and the global offset table relationship. Basically, when we have a Linux binary call into a library function. For example, let's just say we have malloc from C. It won't go directly into malloc's address. Rather, it's going to be jumping into the PLT, which is this procedure linkage table, which is a read-only section of the binary. And then that stub kind of like reads a writable address from the GOAT, which is a writable section of the binary. The GOT then is going to be pointing straight at the function, and if the GOT is writable, we can change the pointer in a GOT slot. We can then like just make calls directly into the malloc. Rather than calling directly into the malloc, we can just make them jump over to our payload instead. Oh. Okay, I think we jumped over a bit. Yeah. Basically, we just mentioned the MFD without modifying the disk. Okay. We can just head over actually straight to the demo, I believe. The tool, basically just entering, we can just search up Aether. Oh, no, it's not even popping up. Here. Okay, so what we are doing right over here, we are calculating all the types of processes which a specific computer, let's say we have the initial access to this specific system. It's going to automatically calculate just all the running processes which are instead, and it's going to tell you basically the user type, if it's root, whatever it is. We can then, let's pick this specific process, and we have around like 20 injection techniques. We of course have all the ptrace ones which we mentioned earlier, LD preload, and we also have maybe like the more quieter primitives which we have, which is process VM write and read v. So we can just go over to the second tab. Let's say we want to do something with ptrace attach. We can go over to the third type of section of the tool. Over here, this is kind of the automatic script. It doesn't actually say that the calculation, it's not calling the function call to happen. Just whenever you run the injection, it's going to be telling you the address which it calculated, if the FFI is actually functional, and it's going to be deploying that daemon. Another interesting feature of Aether is whenever you're in the process of injecting into another, if you're injecting into another process, a Rust daemon is going to be spawning, kind of infecting the init daemon originally, and it's going to be a watchdog over all the processes, and if there's a change in one of the processes, let's say a DL open or DL close, is going to be recalculating the virtual addresses. So let's just go over to the fourth tab. If you press enter, you can see, bar loading currently is probably just parsing the specific file variables. Basically kind of just tells you if it's a success, and here we have the output. But this is just something running locally on my laptop. Basically it's just saying it calculated the base, it deployed the daemon, which of course has the PID first. It's infecting the init daemon. It's going to be telling you that okay, the FFI is okay. If we jump over to 2, we can basically just see the daemon, kind of its health, if it's doing all right. If we jump over to 3, we kind of have like live patches. If we press, for example, enter here, we can just like try and do a hot reload and it restarts. But basically, since the script already finished, there's no need to restart the script from originally. Basically, that's the function of the tool. So, in more technical terms, we have the way that okay, so basically when we wrapped C in Rust, we also had Evasion as a kind of side effect of this strict FFI boundary. Many defense systems, such as EDR agents, they are trained on these specific library calls, function calls, the standard C and standard Rust, which they've started. But when you combine 2 runtimes at the same time, you get something which is fragmented, something which most defense mechanisms they don't know what it is. They're confused, basically. So it hits the boundary, and it's not like a chain call which is invisible. It's just something that it's not a recognizable pattern, which makes it more difficult for the defense system to see if this is an issue which they should page someone about, let's say. Basically, most EDRs are trained on these specific data sets. The typical allocation patterns, typical C things, and Rust ones too. We, of course, though, run into issues specifically when it's coming to Rust, mainly into allocation. What Rust wants is immediately Rust, depending on the type of allocator which it has, it tries carving out its own memory into the operating system. That, of course, can kind of just expose us. And what if it tries, let's say, requesting memory from the OS and disrupting one of the current processes and try and manage its own heap. Basically, what we do is we call mmap directly with mmap anonymous and mmap private to carve out this like dedicated region into memory, so the Rust engine runs there before anything else takes over that memory. And then basically the host and the payload, they never share this space. They just go immediately, they just inject straight into the process. And basically, whenever the address, whenever the specific process dispositions or like cause like missing events from the injection, we save like the current signal state of the process with like proc mask. It continues running the operations and it just takes a detour and doesn't actually finish the script. Otherwise, we mentioned to Damien, it basically just makes sure the payload survives. The essence of Aether in its core is to show that process injection isn't something solved. It's something which is still a real issue against modern defense systems. The techniques are mature. It's just mainly that the toolings are also fragile. Mainly are just like C tools which are tested on a VM, and whenever they're used in production, they fail automatically. So I guess I just kind of created something which shows you that process injection is still something real, is still an issue, and we kind of need to shift the focus from defense systems of basically trying to define runtime analysis and memory analysis. We go into as low as we can into the kernel and try and do an analysis of that. Thanks a lot. That's Aether. Any questions? We finished a bit earlier.
No worries.
Than expected.
Yeah, we have our first question. Here you go, noble sir.
In your experience, how does different methods protect? I'm thinking like Defender and and the different EDR solutions.
What was the question again?
When it comes to the detection,
to
these kind of attacks, how effective are different EDRs?
I mean, of course, it depends on the tier you're kind of on. If you're, for example, on many things like CrowdStrike Falcon, let's say for an example, this could be effective on the lower tiers for an EDR bypass, mainly freer pro tier, whatever the tiers of CrowdStrike are. Against actual enterprise environments, if the EDR is something which does only like audit logs for, let's say it checks if there's any files, it doesn't like it doesn't check the actual memory. If it doesn't check the runtime, this is a tool which can bypass that. But if it's something which, let's say it actually checks out the memory and the runtime, it's a dilemma if it's going to get caught or not. It just completely depends on the EDR. If they see this kind of call stack, which is unknown to itself, it doesn't know if it should report it or if it's just something, it gets confused on what to do. So it basically depends on the situation.
Okay, thanks.
Anyone else? Yes.
Hi. Thank you for the talk. I'm
Over there.
on the other side.
Left.
This guy.
Oh,
This
hi.
guy. Hello.
Hi.
Thank you. So let's call it information gathering you did at the beginning with your tool. The first step you did with your tool, where you enumerated all the processes and look at the techniques you can use. Is that something you could detect? Or is it common that you have a process running around the look here and there?
Basically, what we just did there is you just printed out all the running processes. Basically, maybe it's something which could be detected. It's just like, is it really something which is worth flagging if all your processes were just like written? It's not even calculating its memory addresses. It's just something which is written out.
Okay, so you're basically running PS.
Yeah, basically, yeah.
Okay.
It's not something which usually gets detected.
No, of course. Thank you.
Yeah.
Anyone else? Raise your hand. Firm and high, to the skies.
Oh.
No? Sure? Okay. Thank you very much for a nice talk.